They were larger than life, equipped with the deadliest of weapons. Their world and physiology so alien as to be almost unimaginable. Almost. But the process of attempting to envision the often nasty, brutish, and sometimes short lives of these monsters from the past has never stopped since the first fossil was pulled from the ground.
What we're looking at here is actually a paleo crime scene.
To call Therizinosaurus a monster wouldn't take a stretch of the imagination.
We want to know about their lifestyles, about their habits.
For millions of years, they swam the seas, soared across the skies, and ruled the earth. Now we unearth their secrets. Simple animal life first appeared on Earth some 600 million years ago. Since then, billions of species have existed, but 99.9% of them are now extinct. What they left behind are their fossils, pieces of history that offer clues to life millions of years ago. What can this shattered skull tell us about the 70-million-year-old death of a top marine predator? And why would a giant herbivore need a set of 5-foot claws? And what did flightless dinosaurs do with the covering of feathers? The challenge for scientists is to put flesh back on the bones, to figure out what these monsters really looked like, and how they lived and died, and what their world was like. Using the latest science and technology, we're going to revisit some of the most lethal, terrifying, and bizarre creatures that ever saw the light of day on planet Earth. Hundreds of millions of years of bones lie beneath our feet. It takes a lot of dirty work to get these fossils to give up their secrets.
We're here along the Rocky River in Cleveland, Ohio, looking at a spectacular outcrop of the Cleveland Shale. This beautiful rock layer was deposited at the later part of the Devonian period of geologic time.
The Earth was a radically different place some 400 million years ago. During the Devonian period, all the world's land masses sat around the equator in the form of two supercontinents, Euramerica and Gondwana. A global ocean surrounded these gathered continents, and water covered much of what is today dry land, including Cleveland, Ohio.
The rock layers here represent a deposit at the bottom of a sea that once covered parts of the continent. Geologists call that an epicontinental sea. The sea covered this area at least several hundred feet deep, perhaps even much deeper. The denizens of this sea included fish and a whole host of sharks. These fish preyed upon each other as well as various kinds of invertebrates that lived in the upper parts of the water.
The ocean's most lethal hunter was Dunkleosteus. It belonged to a group of armored predators called placoderms, or platy-skinned fish, that ranged in size from the 30-foot, 4-ton Dunkleosteus to tiny fish no larger than several inches. The placoderms hunted the global seas during the Devonian period, but none rivaled Dunkleosteus.
It's probably the biggest, baddest fish that lived at the end of the Devonian era. It's one of the top predators that's ever swum in the oceans of the Earth since life evolved several billion years ago.
Despite its power and killer whale size, Dunkleosteus's legacy has proven to be fragile. Unlike their Devonian competitors, descendants of the armored placoderms don't exist today. Our clues about Dunkleosteus come from the only physical evidence that survives: fossilized dermal armor that covered the front end of the fish. Armor that, after death, would have dragged Dunkleosteus to the bottom towards preservation. Once the bone settles to the bottom, a protective layer of sediment must cover it in order to fossilize.
In the vast majority of cases, this doesn't happen and the animal just decays away, just like roadkill you might see along a highway.
Fossilization is actually a very rare thing to happen to any given specimen of bone or a shell or a leaf. 99.9% of everything that's ever lived doesn't fossilize, and we don't have it in the fossil record.
If the bone is covered by sediment, then water flowing through the pore spaces of the bone can precipitate minerals out in the little crevices in the bone. Those minerals then turn into a representation of the bone, and all the original organic material decays away.
Fossils of Dunkleosteus's armor plating reveal a beautiful bone structure that made this animal into a model predator.
The top of the head is almost like a drawbridge. There are two hinges on either side of the skull, and there's actually this large soft tissue opening right here. When Dunkleosteus had seen a predator or seen a prey item in front of it and wanted to attack it, it would drop its lower jaws down, but this thing would lift the top of the skull up like a drawbridge.
Based on their study of fossils, scientists restored the musculature to a computer model of Dunkleosteus's skull. They were able to determine that the creature's 4 jaw joints worked in concert to open and close with force and speed.
The length of time it would take to go from a closed mouth to an open gap was less than a 50th of a second. You'd have a big suction formed by the sudden opening, and anything that was swimming in front of it would actually get drawn back towards the mouth. And as soon as these shearing jaws come together, you've got that animal cut in half. Dunkleosteus has a bite force roughly equivalent to Tyrannosaurus rex, which has absolutely the largest bite force that we've ever measured for any vertebrate animal.
This would also rival an alligator's bite, which is the strongest of any living animal. Amazingly, despite how lethal Dunkleosteus was, this placoderm was technically toothless.
Dunkleosteus didn't have teeth like fish such as sharks have or many modern fish. It didn't have a whole bunch of teeth set into a jaw, but instead had protrusions of the bones.
Through natural selection and evolution, the plates that form the lower jaws have actually become thin, elongate like cleaver blades, and you actually have several points coming up on these things. And they were essentially self-sharpening. When the lower jaws moved against the bony plates of the upper jaw, it was just like sharpening a knife.
But much of reconstructing Dunkleosteus remains an act of imagination.
When we're trying to reconstruct an animal like Dunkleosteus here, the only thing you have to work with is the actual skeleton. We have to imagine what the eyes would look like in the eye socket, what sort of covering would there be over the plates that form the teeth, and what sort of skin would be over this body. As a paleontologist, what we want to do is draw modern analogs. When we're looking at things like placoderms, this is a whole group of vertebrates that went extinct. There are no modern analogs to this.
Though armored fish no longer exist, Dunkleosteus's closest living relatives are sharks.
If you can use some kind of modern animal to say something about any kind of behavior, you know, because it truly is speculation. I mean, the suspects are dead.
Essentially what geologists and paleontologists are doing is we're all trying to figure out the plot of the same movie. But that movie has been cut into frames, and those frames have been scattered outside and left out in the weather for hundreds of millions of years. When you go to a geological formation, you have one frame of that movie, and another scientist somewhere else in the world may have the next frame. And then from those individual snippets, you have to try to reconstruct the history of life on Earth with a lot of time missing.
Given nature's incessant predator-prey storyline, the plot often revolves around a murder mystery, as it does in the case of these mosasaur bones tucked away in the basement of the Sternberg Museum of Natural History in Hays, Kansas. The bones of this marine reptile, who hunted the seas some 300 million years after Dunkleosteus, are evidence of a 70-million-year-old regicide, the death of a king.
They were the rulers in the ocean. There was nothing else out there that could threaten a mosasaur except another mosasaur. They were pretty much loners. They were long-distance swimmers. This animal was found in what would have been the middle of the western interior sea, hundreds of miles from the nearest land. He was perfectly adapted for living at sea for his entire life.
Mosasaurs evolved from coastal marine lizards, which hunted in the ocean but returned to the land. During the late Cretaceous, from 89 to 65 million years ago, they took to the sea for good and grew into 50-foot sea monsters. Sea levels were higher in this period. 85% of the Earth was covered in water, as opposed to 71% today. Mosasaurs were more plentiful in these abundant oceans than were the large, more famous dinosaurs that at this time squeezed onto relatively small portions of land. The western interior seaway stretched from Texas into Canada and from the Rockies to the Appalachians.
Roughly the size of the Mediterranean. Very shallow, 600-foot maximum depth, at least in Kansas. So it was a shallow, warm water sea, probably semi-tropical in nature.
This sea was full of life and extremely dangerous.
What we have here is the skull of a mosasaur that was killed, evidently, by a much larger mosasaur. And we can tell that because of things like the bite marks that show up on the bones of this particular skull. It appears that another mosasaur attacked this one. And this guy's about 15 or 16 foot long, probably attacked by something that was 20, 21 foot long, much heavier.
But these guys were midgets compared to the heavyweight of the mosasaur family, Tylosaurus, who at 50 feet was the size of a bus, weighed several tons, and had a 4-foot skull.
The skull is equipped with a very large set of heavy conical teeth that the mosasaur used for seizing and killing animals. They're not cutting teeth. They're not like the teeth of T-Rex that the animal would be tearing apart prey. This guy just swallowed what he caught. He swallowed it whole, very much like a modern snake. He was actually able to ratchet his head around the prey and pull it in complete. One way to look at a mosasaur is to envision it as a large snake. Yes, it still had 4 limbs, but it swam through the water using its tail. Mosasaur has about 130 vertebrae in its body, but 100 of those are in the tail. It literally uses that part of its body to move itself through the water very efficiently.
From the looks of his remains, our smaller mosasaur victim didn't quite retreat efficiently enough.
From the bite marks that we can see on both sides of the skull, it looks like the attacker came from the left side. When he bit down on this mosasaur's skull, it basically collapsed the skull. The 2 jawbones come flattened together against the roof of the mouth, and we see some breakage inside of the teeth that are on the hard palate of the mosasaur. And then it looks like he twisted the head of the smaller mosasaur to the point that the neck was probably broken. We'd have the neck vertebra coming off here at a 45-degree angle, which is very unusual for any kind of a mosasaur specimen. The larger mosasaur probably let him go, and the smaller mosasaur sank to the bottom and was simply preserved as we found it 50 years ago.
This fairly routine 70-million-year-old murder tells us a host of information about the reclusive, confrontational lives of mosasaurs.
I'm sure that the larger mosasaur had no intention of eating this guy. He was too big. Mosasaurs would not attack for food anything larger than they could swallow. In this case, it was a territorial thing or a mating thing. You have two bull mosasaurs going at it with each other. This guy loses because he's the underweight. He's the featherweight compared to the 800-pound gorilla that attacked him. They were solitary animals, for one thing, and maybe just being in proximity to another animal was enough to enable some aggressive activity. We do know, however, that mosasaurs fought with each other fairly consistently. Lots of mosasaur remains have got broken bones or healed bite marks. It's very evident from the fossil record that these things did not live together harmoniously. They tended to fight each other a lot.
So to pry open a door onto the past, a paleontologist must be part forensic pathologist.
We can see bite marks, or we can see the teeth of other animals, or evidence of digestion, or pathologies that may include things like cancer or even arthritis in some animals. Those are important bits of information that tell us more about these creatures and how they lived.
But just what exactly was going on inside a mosasaur's gigantic head?
Brain size is small. Even the largest mosasaurs, the brain was not much larger than, say, your index finger. A lot of the responses, a lot of the activity of a mosasaur was purely instinctive. They didn't sit around thinking about the condition of the world or anything. They were active predators, and that's what they did.
The mosasaurs dominated the seas before becoming extinct 65 million years ago. But mosasaurs might not seem quite as bizarre as giant insects, like this dragonfly that grew to the size of a hawk and hunted the skies of the Carboniferous period 300 million years ago. We go through a great deal of effort to control our environments and to make them comfortable inside and out. But there are few things that destroy our peace of mind like insects. And yet, they're everywhere, above us, beneath our feet, and in our food. But it could be worse, much worse. They could be giants. Is this just fantasy, paranoid 1950s style science fiction? Maybe so, but for a period in Earth's distant history, giant insects were a fact of life.
Imagine a huge dragonfly with a wingspan of about 3 feet.
This dragonfly, Meganeura, was one of the most aggressive predators 300 million years ago.
Paleontologists now find mostly wings as fossils because those are the sturdiest parts of the body that usually survive fossilization. So for all the giants, there are only some body parts found, and the paleontologists have to puzzle the pieces together and guess the actual size of the animal from scaling relationships of living animals or complete fossils that they found from other times.
During the Carboniferous period, many parts of the Earth were a swampy smorgasbord for this oversized insect.
The environment was pretty warm, and it was a time where a lot of plants started to grow. The first forest existed. The world was very humid and moist, so it was a time where there was a lot of abundance of new habitats and abundance of food and shelter.
Meganeura buzzed overhead, preying on insects and even small amphibians that it snatched up with its legs. On the ground below, Arthropleura, a 6-foot giant millipede-like creature, skittered through the swamps on 30 pairs of legs. The largest land arthropod may have eaten as much as 1 ton of vegetation a year. There was no predator on land that was big enough or strong enough to break through its hard exoskeleton.
We call it a sow bug on steroids. It's not an insect, but it's related to parts of arthropods. It includes the crustaceans and the millipedes. So it would have reminded you of a centipede or a sow bug, but it's gigantic, 8 to 9 feet long in some specimens.
There weren't many predators around on the land during the Carboniferous, so it was a very good time to be an invertebrate.
It's certainly the largest land animal alive at that time, and any kind of either plant or animal debris that it wanted to eat, it could eat, but it doesn't need to be a great predator at a time when there's so much food available. The world was ruled by arthropods still. Even the cockroaches are huge, they were a foot long.
Scientists suspected that plentiful food and relative safety were not enough to make superbugs possible. If that were all it took, they might still be around today. But there was another significant environmental difference during the Carboniferous period.
Plant life was doing so well in the Carboniferous, pumping lots of oxygen into the atmosphere. Part of it may also be that a lot of these forests were growing in wet, swampy environments, and when that plant material is then preserved in those environments, you're sequestering carbon in those environments. So if you're taking out carbon from the atmosphere, you're changing the ratio between oxygen and carbon in the atmosphere.
Researchers suspected that higher oxygen levels during the Carboniferous period were key to insect growth, but they didn't understand the connection. The secret to this mystery is under investigation just outside of Chicago, Illinois, at the Argonne National Laboratory, one of the U.S. Department of Energy's largest research centers. Scientists here suspect that the key to size has to do with how insects supply their bodies with oxygen, and are looking for answers about insect respiration in this tiny beetle's body.
The first thing that I do is to take the beetle and knock him out. I simply put him to sleep by giving him nitrogen gas. This is just temporary. It doesn't hurt the animal at all.
Once the beetle has been properly subdued, he's ready for his close-up.
What I'm doing here is placing the beetle on a stand that we can control from the outside. So we can move it up and down and side to side and position where we want it in the X-ray beam.
Searching Station C. Exit immediately.
This tiny bug sits at the imaging end of one of the world's most massive X-ray machines.
This is the advanced photon source. It is what we call a third-generation synchrotron. Its function is to produce very powerful X-rays.
The synchrotron generates X-rays 1 billion times stronger than a hospital X-ray machine by accelerating electrons around a 1.1 kilometer track at close to the speed of light and harnessing the X-rays they emit. Teams of researchers work at stations around the track, accessing the 2 millimeter square laser-like X-rays for their experiments.
What's the species again?
This is Tenebrio molitor. It's a mealworm beetle.
Because of the strength of these X-rays, our team can see the beetle's respiratory system in action to understand how it works and how this system limits insect size.
The analogy here is before we had X-rays in general, we knew that there was anatomy, we knew there, you have bones and muscles, but it'd be like only being able to dissect a dead human to go into being able to see the muscle movement and the bone movement all at once. That's how big of a leap this is for small animals like this.
And the tracheal tubes, the key to insect breathing, turn out to be critical to insect size. Unlike vertebrates, who get oxygen from their lungs to their cells in their bloodstream, insects transport oxygen through a series of tracheal tubes that runs from the surface of their exoskeletons out to their extremities where they dead end.
And one of the trachea here is actually pumping. So you can see that the band is contracting and expanding.
This tracheal system is incredibly efficient at delivering oxygen, but with the help of the detailed X-rays, researchers were able to shed light on the limitations of this breathing design.
With the high-resolution X-rays, we can measure their anatomy and measure their details with precision that we've never done before.
What researchers learned from their measurements of the trachea of tiny beetles and specimens as much as 1,000 times larger is that as you scale up in bug size, the trachea must grow disproportionately larger to maintain oxygen supplies. Insects' bodies place an upper limit on this growth.
There's a very unique feature in insects, and this is that they have an exoskeleton. So they have a hard shell that confines the space for tissue inside of the body.
So what they have to do is they have to pack all the tissue, all the things that they need to survive within this confined area that they have. And there are few places in the body where this confinement is actually very important.
The critical junctures in insects occur at their joints, areas where their exoskeletons pinch and they end up with traffic jams of trachea and tissue.
It's right here where the leg is attached to the body. Through this orifice, insects have to supply the air. They have to connect muscles by tendons. They have to supply insect blood through that orifice into the leg.
As beetles get bigger, the tracheal tubes begin to fill up the space in this orifice. A little math led researchers to a prediction of maximum bug size.
When we increase the tracheal dimensions to a point where about 90% of this orifice is covered by a tracheal tube, the hypothetical beetle is about 16, 17 centimeters large. And this is about the size of the largest beetle that we have on Earth nowadays. It's a longhorn beetle. It's called Titanus, and it's a Central American animal.
In our environment, bugs can get no bigger. But what if you had an environment 300 million years ago when oxygen levels were markedly higher? Oxygen levels in the Carboniferous atmosphere increased over time until they reached levels of between 30 and 35%, as opposed to today's 20% atmospheric oxygen concentrations.
Because we had a better oxygen supply into those structures, insects could actually decrease the size and the dimensions of those tracheal tubes.
Smaller tracheal tubes left more space for other tissues to grow.
They essentially were superfueled arthropods during the Carboniferous with this enhanced level of oxygen.
These theories are currently being put to the test.
What my colleagues are doing at Arizona State University is rearing flies or other insects under different oxygen concentrations and see if they actually change their size or their tracheal dimensions. For example, fruit flies under higher and lower oxygen concentrations. And what they saw is that, yes, they get bigger as oxygen supply is higher, and they also reduce their tracheal dimensions.
The giant insects and arthropods, like most eccentric life forms on the planet, were a passing phenomenon. But their creeping, crawling insect descendants are still with us and comprise roughly 95% of life on land. Birds are also still with us, and the connection between feathers and flight has long been understood. But new revelations in the fossil record are shaking up what we know about the evolution of feathers and which past monsters wore a downy coat.
Timmy, what is it? It's a velociraptor.
Raptors. They've been immortalized on screen as extra-large, cunning super predators.
It's certainly an animal that would have been a formidable predator and not an animal you would want to run into in a back alley.
Moreover, raptors look like something terrifying sent over from central casting. Swift, stealthy, with sickle-shaped claws on their back feet, powerful arms, and that chilling reptilian look. But the truth is often stranger and more complex than fiction. Most raptors were relatively small, and recent evidence indicates these dromaeosaurs, or swift reptiles, were actually related to birds and were covered in feathers.
It is a shock. You go from these scaly reptiles to what might, in an instance like Velociraptor, be this really angry chicken.
The angry chicken. It just doesn't have that marquee ring to it, but it does have the ring of truth, because feathers first appeared on dinosaurs. As birds evolved from dinosaurs, feathers became more substantial in order to be useful for flight.
There are very few differences that you could point to between, say, a chicken and a T-Rex. They have very, very similar anatomies, and that's because they have a common ancestor, and that common ancestor is not very far back in their lineage.
This split on the evolutionary tree between the non-avian theropod dinosaurs and their smaller cousins, the raptors, and the first birds, Archaeopteryx, can't be pinpointed in time. But the two groups, one that would never fly and one that would dominate the air, share many physical characteristics, including feathers.
The first sort of feathered dinosaurs that were clearly not birds were found around 1995. These fossils were coming out of China that had these really sort of halos of kind of feather fuzz around them, sort of very downy-like feathers. So it's not these asymmetrical, really modern feathers that most people are familiar with on birds.
More recently, Alan Turner made a discovery that extended this downy covering to more flightless theropod dinosaurs, velociraptors found in Mongolia.
This is the ulna of a velociraptor, so it's one of the lower limb bones, or the forelimb. And I found these bumps, these quill knobs along the back of the ulna, which is where the ligament that attaches the feather embeds itself in the bone. They're actually quite small, so I felt them actually before I saw them.
And these quill knobs can be found on modern birds.
What's interesting about Velociraptor is it's one of the larger of the dromaeosaurs known that we actually have direct fossil evidence for its feathers. We have good reason to have predicted that these animals would have been feathered because we know their earlier, smaller relatives had feathers.
Beyond cosmetics, these feathers are a further confirmation of the close connection between raptors and birds.
They're not just dinosaurs, but they're actually a particular kind of dinosaur. They're embedded in the tree of life within the group of predatory dinosaurs. They're in fact more closely related to things like Velociraptor than Velociraptor is related to something like Tyrannosaurus.
Though feathers are perhaps the most dramatic connection between raptors and birds, there are many similarities that are not just skin deep.
When you look at a bird today, a lot of what you see is in fact dinosaur and not as much bird as you think. The hollow bones are in fact a theropod feature. Those are around for 210 million years. The wishbone that you see within a bird, that's also a theropod feature, evolved long before flight ever evolved.
All those guys have, for example, a specialized wrist bone called a semilunic carpal. It does a big sort of flex motion like this, which in a predatory dinosaur is useful for grabbing prey. It is exactly the same motion that a bird does in their downstroke of a flight. And that's one of many anatomical characters that show us that birds are dinosaurs.
But why did these features lead to flight in some dinosaurs and not in others?
The whys of evolution are not an easy question for science to address because sometimes there may not be a why. It may just be sort of a happenstance of evolution that some of these features evolved and then happen to be advantageous. What we do know, at least about these features, is that they didn't evolve for flight, and they just happen to be able to kind of be utilized for that behavior in the earliest birds.
But if feathers appeared in raptors, for whom flight was an aerodynamic impossibility, did they serve some other purpose?
Right now, sort of the leading ideas about why feathers might have evolved have to do with their role in thermoregulation. Around the time that we see the first feathers showing up in the fossil record, within these group of dinosaurs, you're seeing a big shift from being a very big theropod like Allosaurus to going to be very small. So you're going from being multiple tons in mass to being maybe just 10 or 15 pounds. As you get smaller, it's much harder to maintain high body temperatures, and these were probably fairly active animals. And the evolution of feathers was somehow adaptive for maintaining body temperature as these animals got small evolutionarily.
Flight feathers were the last stages of feather evolution. Millions of years later, the evolution of the modern feather signaled the turning point from non-avian dinosaurs to Archaeopteryx, an animal that is recognizable as one of the earliest birds.
What we're looking at here are casts of the first and probably one of the best Archaeopteryx specimens found. These are preserved in very fine-grained limestones, and that preserved these impressions of the feathers that these animals had. What's probably most significant is all the things it doesn't have. You can look at its skull, and it still has teeth, just like all the other theropods do, but not like modern birds. So it really is this sort of kind of perfect transitionary animal.
Just as these prehistoric creatures were constantly evolving, our understanding of them is almost always changing as well. Two seemingly disparate disciplines, art and science, intersect to reveal just how much and how little we really know about these ancient monsters. Therizinosaurus clawed its way into the fossil record, literally. The first evidence of these freakish creatures, a giant 5-foot claw, was discovered in the late 1940s.
The first thing they found were a few claws from the hand, and they were so unlike anything we'd ever seen before that the scientists who named them thought that they belonged to a turtle.
When paleontologists discover any new creature, one of the first questions they ask is, what did it look like? Paleo artists like Patrick O'Brien, who illustrate for museums and publications, are instrumental in this fleshing out process.
So I'm picturing it must have been some truly huge prehistoric turtle with these giant claws on his 4 feet.
But the turtle connection proved to be a mistake. The claws were actually the first clues to the discovery of a bizarre new animal.
They began finding more and more pieces of more and more dinosaurs that were closely related to Therizinosaurus. So our image of what this animal was evolved a lot through time.
So it turned out to be a new and strange kind of theropod dinosaur, and not a turtle at all.
Therizinosaurus, who lived 70 to 75 million years ago during the Cretaceous period, was a theropod, a group of almost exclusively carnivorous dinosaurs that included T-Rex. But at 40 feet long and 3 to 6 tons, Therizinosaurus's body had some odd features: an extended neck, a beaked head, and a potbelly that are typical not of carnivores, but of herbivores. Scientists were baffled.
Therizinosaurs were an incredibly bizarre group of raptor dinosaurs. They weren't recognized as raptor dinosaurs for the first 50 years that they were discovered because they were so different from any other dinosaur we'd ever seen. The only way that the story got resolved was when we discovered exceptionally primitive forms. And those animals looked so much like raptor dinosaurs, but started to show some adaptations towards animals like Therizinosaurus that we were able to actually piece back the history and get at what the ancestry of these animals were.
The missing link in this mystery is on display at the Utah Museum of Natural History. Discovered in 2005, Falcarius is the most primitive specimen of the Therizinosaur group. It lived 130 million years ago and marks the transition between the predatory raptor ancestors and their plant-eating Therizinosaur descendants.
Falcarius still maintains a lot of anatomy that's similar to, say, Velociraptor. It still has a small body, powerful arms, but small claws. It is showing some changes that allow us to place it within Therizinosaurus. Its neck is starting to get longer, its head is starting to get longer. But basically, when you look at the skeleton of Falcarius, it's a raptor dinosaur with just a few changes that tell us that it just began to switch towards a new lifestyle.
Falcarius's leaf-shaped teeth are the most telling pieces of its anatomy that indicate it had begun eating plants.
The teeth are very well adapted for eating plants rather than eating meat.
These first steps towards herbivory grew more pronounced over millions of years of evolution.
There's about a 70 million year difference between Falcarius and Therizinosaurus. If you looked at the two of them side by side, you probably wouldn't recognize that they were closely related.
Therizinosaurus's huge size and bizarre shape make it a good candidate for a full-scale rendering. But rendering is an ambiguous process. Representations of dinosaurs must include the illustrator's best guesses of coloration, skin covering, and even behavior based on the scientific evidence.
On the computer, I created this drawing of a Therizinosaurus skull so that I could try out different soft tissues. First, I created an outline of the soft tissues with the muscles and skin, and then I thought I would try to sort of bird-like headgear, which is plausible on Therizinosaurus. They were feathered dinosaurs, and their relatives did evolve into birds. I also thought I would try to put more of a lizard-like headgear. This is exactly what modern-day iguanas have on the tops of their heads.
Artistic judgment and scientific judgment may not be as far apart as we think. In both processes, what we know about these long-extinct creatures is an approximation based on analogies and assumptions until definitive evidence is dug up that furthers knowledge.
Science is this ongoing intellectual pursuit, and that's kind of the beauty of it. You keep gathering data and keep putting forth these hypotheses and keep finding new lines of evidence.
All along the way, this is a self-correcting scientific process. We find better specimens. We often have to revise what we thought about animals. But that's fine. That's the way it's supposed to be.
There is fossil evidence that suggests features of Therizinosaurus's form and some behavioral surprises.
Most of the scientists think that Therizinosaurs probably had a beak because you can see that they have teeth in the skull, but only in this back part here for chewing, and in the front they don't have any teeth at all. So they probably had a beak that looked something like that.
Satisfied with these choices, Patrick begins to work with the whole animal. But the function of the massive claws is the thorniest issue.
Some people have suggested they use these for spearing fish, and the hypotheses kind of run wild. They may have been used to scare away predators. They don't appear to be very good for actual defense. They may have also been for sexual selection. They may have been a mating signal or just a sexy look for a Therizinosaur.
Ultimately, Patrick's painted version incorporates the idea of the claws as food gatherers. Scientists theorize that Therizinosaurus may have pulled high vegetation down to its mouth to eat. He has also given the creature a potbelly, customary for animals that digest huge amounts of vegetation.
Plants are much harder to metabolize for animals. Think of it, when you're eating a cow, you're turning a cow into human. That's kind of a smaller step than turning lettuce into a human. So it takes more time and more specialization than to be an herbivore. And one of the ways that herbivores deal with that issue is to have larger stomachs where they can leave the food in there longer to get more of the nutrients out of it.
Before the portrait is complete, Patrick must contend with one last detail that remains speculative.
Most of the fossils of the close relatives of Therizinosaurus were found with feather impressions in the dirt. And so it's assumed that Therizinosaurus were also feathered, and they were probably these sort of downy, sort of thin feathers. They weren't flight feathers. It certainly wasn't a flying creature.
And were the feathers brightly colored for display or muted for camouflage? Since we don't have any 70-million-year-old Therizinosaur feathers, color must be determined by deduction.
Therizinosaurs were very large. They probably weren't trying to bother to hide from anybody. So I'm going to guess that they're brightly colored with bright, bold patterns on them to impress other Therizinosaurs.
To work with extinct creatures, you have to accept that a certain amount of mystery will never go away.
It's all very speculative. Modern-day creatures do things that you would never guess just from looking at their anatomy. Modern-day whales, who can dive to such great depths for such long periods of time, if you only were looking at the bones of these animals and you knew something about mammals, you wouldn't guess that a mammal could do that, because mammals can't do that. They can't dive to such great depths and hold their breath for 10 minutes, 20 minutes at a time, and yet they do. So perhaps there were things like that the dinosaurs were doing that we just don't really know, and we just can't know. We probably will never know. That's looking pretty good.
Life on the ground in the Cretaceous was no picnic, but the dinosaurs couldn't look to the sky and imagine a kinder, gentler world. The sky was full of pterosaurs, some as big as small planes, and they weren't vegetarians.